Hi, welcome to Chapter 20, Electrochemistry Overview Part 4, the last part of this chapter, where we'll talk about batteries and fuel cells, corrosion, and electrolysis. So some applications of our voltaic cells are batteries. Electrochemistry can be applied as follows. You can make batteries, which are a portable, self-contained electrochemical power source. That could be one or more voltaic cells. So here, this battery here is one cell, but this flashlight needs more voltage, so you have two cells set up in series. Batteries can be primary cells, which cannot be recharged, they go dead, or secondary cells, which can be recharged. You could also use electrochemistry to prevent corrosion and do something called electrolysis. So some example of batteries are your lead acid batteries. These are normally in cars, regular electric cars. And in this case, you have your reactants and products are solids. So because of that, your Q is going to be equal to 1, and your cell potential is going to be independent of the concentrations. And because they are solids, you can have a consistent voltage as you're using the battery. You're not going to see a huge voltage drop. And what's really nice about them is you can recharge them. However, there are some drawbacks. They're made with lead and sulfuric acid, and because they're made with lead, they are relatively heavy. Alkaline batteries are the most common batteries that you use. So like if you're putting batteries in a toy or something like that, it's probably an alkaline battery. Then you have your nickel cadmium or nickel metal hydrate batteries, and these are lightweight, rechargeable. The problem was that cadmium is toxic, so they are replacing it with hydrides. And probably one of the most recent and most widely used batteries are your lithium-ion batteries. These are rechargeable because lithium is such a tiny element. It is very light, and you can produce more voltage than your nickel-based batteries. So here's a drawing of your lead-acid battery. And you see here you have your anode is the red and your cathode is the blue. They're both solids. And then you have sulfuric acid kind of filling in the gaps. Here is your regular alkaline battery. You have an anode, which is zinc plus potassium hydroxide. And you have a cathode, which is manganese 2, a manganese 4 oxide plus graphite. And this is sealed in a metal container. Then you have your lithium-ion batteries, and you see here you're getting 3.7 volts. They generate a large amount of voltage, and they are relatively light, so that's why these are so liked. So how does it work? So you have this graphite anode that contains layers of carbon atoms, which are the black spheres, and lithium plus ions can move in out in between these layers. Then they go through this membrane here, and they come on this side here. And in this one, the blue spheres are cobalt and the red are oxygens. Again, you have these layers, and the lithium can move in and out of the spaces between. Your fuel cell is when in general, when we have fuel, we burn it to take that heat energy and convert it to electric energy. That whole conversion is only 40% efficient. You lose a lot of heat. So it's not a very efficient use of a fuel. The direct conversion of chemical to electric energy is expected to be more efficient and is the basis of what we call fuel cells. Fuel cells are not batteries because you have to constantly supply them with a source. Now, your battery is a sealed container, and the reaction happens inside that. Your fuel cells, you have to constantly put something in so that you could get this energy out. So hydrogen fuel cells, you might have heard of these. These are commonly used in electric cars. It is a cell that is hydrogen and oxygen, and it forms water. The cells are twice as efficient as combustion, and they use hydrogen gas as a fuel and oxygen from the air. So you see you have to constantly put hydrogen in, and you get oxygen from the air, and then the reaction occurs, it makes water, you get your voltage, and then you have oxygen and water come out, and excess hydrogen comes out here. This is very expensive because in order to speed this reaction up, you have to use platinum. Platinum is one of the most expensive metals. Corrosion. Corrosion is oxidation. So one of the common names of corrosion is rusting. This is when iron oxidizes. So here we have a piece of iron and a droplet of water sitting on it. So your iron will turn into iron Fe2 plus 2 electrons. The Fe2 plus will go into the water droplet. The electrons will move across your iron, come up here, and then they will react with your Fe2 plus, making it Fe3 plus, which then reacts with oxygen and makes that rust brown color substance that piles up on your iron. How do you prevent this rusting or corrosion from occurring? Well, there's two ways you could do that. So you have your cathodic protection, which occurs because zinc is more readily oxidized. So this metal is sacrificed to keep the iron rusted. So basically, here is your iron, and they put a thin layer of zinc on there. Then your water droplet's sitting there. If we zoom in here, zinc is your anode, and your iron would be your cathode here. And what happens is the zinc will react before the iron does. So the iron will not rust. The zinc will, the zinc coating oxidizes, and the iron does not. Another type of corrosion protection is using a sacrificial anode. So here are some pipes that are in the ground, which water could be in the ground. So to prevent them from rusting, they attach with a wire a piece of metal that would oxidize quicker. So in this case, it's magnesium. The next application is electrolysis. And this is used in a lot of gold, like when you want to metal plate things, you use electrolysis. So here you see a diagram where you have molten sodium chloride. So electrolysis can also be used to separate elements from their compounds. So if you want to get sodium and chlorine gas, if you could get your salt to be molten, so basically melt it, then run a current through it, you can actually get solid or actually liquid sodium out, and the bubbles will be your chlorine gas, and you can collect them and have a nice pure sample of your elements. So electrolysis can be used to separate elements from their compounds, or it could be used to deposit coatings on stuff. So in this diagram here, you had a steel object, and you're depositing a coating of nickel on it. So in electrolysis, though, you are applying an electrical source. You have some voltage source. So a non-spontaneous reaction can occur if you have an outside electricity that is used to drive the reaction. The use of electrical energy to create a chemical reaction is called electrolysis. This process can be used to decompose compounds like water or like our sodium chloride up here, or to force a redox reaction to occur in the reverse direction called electroplating. When a compound decomposes or when the electrolysis occurs, the substance with the greater reduction potential will form at the negative electrode, and the substance with the lower reduction potential will form at the positive electrode. So remember, your negative electrode was your anode, and your positive electrode was your cathode. So if you see here, you're plating this substance with nickel. So electrolysis and stoichiometry. So remember, a coulomb is a measure of charge, and what we have here is this equation where you have amps times your time will give you your charge. So amps is how we measure current. So if we want to get Q, you're going to just measure your current times time, amp. So this would be I, and this is T. That is also equal to NF, where F is your Faraday constant, which is the charge of 1 mole of electrons. And N is different than it is in the previous section, where now it's the moles of electrons that travel through the wire at a given time. So it's not the total moles in the ballast. redox reaction. It's the amount of electrons traveling through the wire. A is your current measured in amps, and T is time. So electroplating is used to increase corrosion resistance. You can put a thin layer of a metal on top that would protect the metal underneath. Or it could be used to improve a metal's beauty by adding a thin layer of the metal. So if you have like jewelry and it's called gold plated, it has a thin layer of gold on the outside, but underneath it is some other metal. So in order to determine the time it takes or the amount of substance that will deposit, we use that a coulomb is equal to amps times seconds. So this is where we get our the equation on the previous page. Okay. So, and a volt is equal to a joule over a coulomb. And that is the end of part 4.